You have 48 hours to do the impossible. October 19th, 2024, 2:47 a.m. Universal Time. You're the mission controller for NASA's Mars Reconnaissance Orbiter, staring at telemetry data that makes no sense. A glowing object just appeared in your spacecraft's field of view, moving at 200,000 miles per hour through the Martian atmosphere. Not a meteor, not a satellite malfunction. This is 3I/Atlas, an interstellar comet that's been travelling through this galaxy for millions of years, and it's about to make its closest approach to Mars in exactly 47 hours and 13 minutes. Your spacecraft wasn't designed for this. Your cameras are pointing the wrong direction. Your instruments are calibrated for Martian geology, not alien chemistry. But this is a once-in-civilization opportunity. Miss this window, and 3I/Atlas disappears into deep space forever, taking its secrets with it. What happens next rewrites the rulebook on space exploration. The images your spacecraft captures reveal jets of gas exploding from the comet's nucleus, a mysterious multicolored glow that scientists can't explain, and chemical fingerprints from a star system billions of miles away. If deep space mysteries like this get your pulse racing, this channel is for you. We break down the universe's biggest discoveries in ways that make you feel like you're right there in mission control. Like this video if you want more content like this. Subscribe to join our community of space enthusiasts, and hit that bell, but only if you're genuinely excited to explore the cosmos with us every week. But before we dive into those 48 hours of chaos, you need to understand what makes 3I/Atlas fundamentally different from anything we've ever studied. This isn't just another comet, it's a messenger from another star system. You need to understand something fundamental about our solar system. We thought we knew all the neighbours. For decades, astronomers catalogued every asteroid, every comet, every chunk of rock that called our cosmic neighbourhood home. These objects all shared one thing: they were born here, 4.6 billion years ago, from the same cloud of gas and dust that formed the Sun. Their orbits followed predictable patterns, ellipses that loop around our star like clockwork. Then, on October 19th, 2019 astronomer Gennady Borisov spotted something that shattered that assumption. Using a telescope he built himself in Crimea, he detected a comet with an orbital eccentricity of 3.2. To put that in perspective, every object naturally bound to our solar system has an eccentricity below 1.0. Anything above that number means one thing: this object isn't from here. The International Astronomical Union gave it the designation 2I/Borisov the I, standing for interstellar. It was only the second confirmed visitor from beyond our solar system, following the mysterious Oumuamua 2 years earlier. But unlike Oumuamua, which tumbled through too quickly for detailed study, 2I/Borisov gave scientists a gift time. You're watching trajectory calculations light up your screen in real time. The comet's path cuts through the inner solar system at a hyperbolic angle, meaning it's not orbiting the Sun, it's falling past it, slingshot around our star, and shooting back out into interstellar space. NASA's calculations show it entered our solar system from the direction of Cassiopeia, travelling for potentially millions of years before we ever saw it. Where it came from exactly, we still don't know. The stellar neighbourhood in that direction contains dozens of candidate star systems. Here's what makes your pulse quicken. Spectroscopic analysis from the Hubble Space Telescope revealed 2I/Borisov contains water vapour, carbon monoxide, and cyanogen chemicals common in comets from our solar system, but the ratios are wrong. The carbon to oxygen ratio sits significantly higher than what you'd find in typical Kuiper Belt objects. Dr. Martin Cordner from NASA's Goddard Space Flight Center noted in his published research that this suggests 2I/Borisov formed in a colder, more carbon-rich environment than anything we have here. Think about that you're looking at frozen materials that condensed around another star, in conditions fundamentally different from the cradle that birthed Earth. But 2I/Borisov passed through quickly, making its closest approach to the Sun on December 8th, 2019 at a distance of 2 AU, twice Earth's distance from the Sun. Ground-based telescopes captured what they could. Space telescopes swiveled to grab precious observation time. And then it was gone, fading as it accelerated back toward the darkness between stars. Fast forward to 2024. You're monitoring deep space detection networks when the alerts start flooding in. This time, the designation is 3I/Atlas, discovered by the Asteroid Terrestrial Impact Last Alert System in Hawaii. And this one has a trajectory that brings it closer to Mars than 2I/Borisov ever got to any major body in our solar system. The numbers make your hands shake. Closest approach, distance to Mars just 87,000 miles. For context, that's roughly 1/3 the distance between Earth and our Moon. Your spacecraft orbiting Mars, the Mars Reconnaissance Orbiter, the MAVEN probe, even the aging Mars Odyssey have cameras and spectrometers that could resolve surface features on 3I/Atlas if you can point them correctly. But there's a problem. Actually, several problems stacking up like dominoes about to fall. First, these spacecraft were designed to study Mars, not fast-moving comets. Their instruments are calibrated for Martian geology, atmospheric composition, polar ice caps, not for capturing an object moving at 54 kilometers per second relative to Mars. Second, the observation window is insanely narrow. You have two optimal points. One when 3I/Atlas approaches Mars, travelling sunward, and another when it whips around and exits, already accelerating back to interstellar space. Miss those windows, and the comet becomes just another faint smudge of light against the star field. Third communication delay from Mars to Earth is approximately 20 minutes. You can't fly these spacecraft like a drone operator with a joystick. Every command needs to be pre-programmed, uploaded, and executed autonomously. Can you feel the weight of this decision? You're staring at a visitor from another star system, carrying frozen records of planetary formation from a solar neighborhood we might never visit, passing close enough to study with unprecedented detail. But your tools are already committed to other missions. Your budgets are allocated. Your spacecraft are old Mars Reconnaissance Orbiter, launched in 2005, making it nearly 20 years old by this point. And yet, Dr. Leslie Tampari, project scientist for Mars Reconnaissance Orbiter, makes the call, "We're doing this." Those three words ripple through mission control. Engineers who spent years perfecting Martian surface maps are now recalculating pointing angles for a comet moving faster than any object their spacecraft has ever tracked. Astronomers who studied dust storms on Mars are now analysing spectroscopic data to predict what wavelengths will best capture 3I/Atlas's mysterious glow. You have one shot at this. The encounter geometry only works if everything goes perfectly. And perfect in space exploration is a word that makes veterans nervous. But here's the thing about the impossible sometimes. You don't have the luxury of waiting for better conditions. Sometimes, the universe delivers an opportunity so rare, so scientifically valuable, that you take the shot even when the odds look grim. Because if you don't, you live with the regret of letting a cosmic messenger slip through your fingers. The countdown clock ticks down. 48 hours until closest approach. You've got work to do. So how do you reprogram a Martian spacecraft to hunt an interstellar comet in less than 2 days? The answer involves a level of improvisation that would make any mission planner sweat and reveals just how adaptable these billion-dollar machines really are when pushed to their limits. The clock shows 46 hours and 22 minutes until closest approach. You're sitting in a conference room at NASA's Jet Propulsion Laboratory in Pasadena, California, surrounded by engineers who look like they haven't slept in days. Because they haven't. Here's what normally happens when you want to retarget a spacecraft. You submit a proposal, wait for peer review, allocate observation time months in advance, run simulations, test command sequences, and then maybe you get approval to proceed. The whole process typically takes 6 to 12 months. You have 2 days. Dr. Richard Zurich, Chief Scientist for the Mars Program Office, stands at the whiteboard sketching orbital mechanics with a dry erase marker. The issue, he explains, pointing to a diagram that looks like spaghetti thrown at a wall, is that MRO's high-res camera has a field of view of just 1.14 degrees. At the projected flyby distance, 3I/Atlas will cross that field in approximately 8 seconds. 8 seconds. You've got 8 seconds to capture the sharpest images ever taken of an interstellar object, and your camera needs to track a target moving at angular velocities it was never designed to handle. Think about trying to photograph a bullet in flight with a telephoto lens. Now imagine that bullet is 87,000 miles away, and you're controlling the camera with a 20-minute communication delay. That's the challenge sitting in front of you. The Mars Reconnaissance Orbiter's high-res camera, the high-resolution imaging science experiment, can resolve objects as small as 3 feet across on the Martian surface. It's the reason we have those stunning images of Spirit and Opportunity rovers sitting on rusty plains, of avalanches cascading down polar cliffs, of weird spiral patterns in the polar ice caps. But it achieves that resolution by using a technique called push-broom scanning. As the spacecraft orbits Mars, the camera builds up images line by line, like an old-fashioned fax machine. It's perfect for mapping stationary terrain. It's terrible for tracking objects that won't stay still. We need to flip the script, says Sarah Milkovich, high-rise investigation scientist. Her team proposes something audacious instead of using MRO's usual fixed pointing mode. They'll use the spacecraft's reaction wheels, the devices that control its orientation, to slew the entire satellite, following 3I/Atlas across the sky while simultaneously capturing images. It's like trying to draw a straight line while running on a treadmill. The math gets uploaded to supercomputers at JPL. Trajectory specialists feed in 3I/Atlas's predicted path, factoring in gravitational perturbations from Mars, the Sun, even Jupiter's distant pull. They calculate pointing angles down to microradians, that's 1/millionth of a radian, an angular measurement so precise that an error of just 10 microradians would cause the camera to miss the comet entirely. But here's where it gets complicated. You're not just photographing 3I/Atlas, you're trying to study it. That means coordinating multiple instruments simultaneously, while HiRISE captures visible light images. You want CRISM, the Compact Reconnaissance Imaging Spectrometer for Mars, to analyze the comet's spectral signature, breaking down its reflected sunlight into constituent wavelengths that reveal chemical composition. You want MRO's context camera to grab wide-angle shots that show 3I/Atlas's coma and tail structure, and ideally, you want MAVEN the Mars atmosphere and Volatile Evolution spacecraft to use its ultraviolet spectrograph to detect any outgassing that HiRISE might miss. Each of these instruments operates independently. Each has its own pointing requirements, its own data buffer limitations, its own power constraints. Normally, mission planners spend weeks choreographing such observations. You've got 38 hours left. Here's a question: have you ever had to completely change plans at the last minute for something important? Maybe reroute a trip, reschedule a major event. That feeling of controlled chaos, that's what's happening in mission control. Except the stakes are millions of dollars in spacecraft operations and a scientific opportunity that won't repeat in your lifetime. The team splits into subgroups. One tackles the command sequence for MRO, writing code that will autonomously execute during the flyby. Another models 3I/Atlas's brightness to determine optimal exposure times too short and the comet appears as a faint smudge. Too long, and the image motion blurs everything into uselessness. A third group coordinates with the Deep Space Network, the global array of radio antennas that communicate with distant spacecraft, ensuring that data downlink windows align perfectly with the observation period. At hour 32 before closest approach, a problem emerges. MRO's orbital position during the optimal observation window puts the spacecraft in Mars's shadow for 14 minutes, right when 3I/Atlas makes its nearest pass. In shadow, solar panels generate zero power. The spacecraft runs on batteries, which limits how many instruments can operate simultaneously. You watch as power engineers recalculate energy budgets down to the watt. HiRISE consumes 65 watts during operation. CRISM needs 50 watts. The reaction wheels controlling spacecraft orientation draw another 40 watts under active slewing. The radio transmitter essential for sending data back to Earth pulls 100 watts. The numbers don't add up. You're 55 watts short of the battery's safe discharge limit. Someone suggests turning off the spacecraft's heaters. Mars orbit is cold temperatures plunge to minus 130 degrees Fahrenheit in shadow. Without heaters, sensitive electronics risk thermal shock, but Dr. Dan Klaus, MRO's spacecraft manager, makes a calculated gamble. The flyby lasts 14 minutes. Our thermal models show we can survive that cold exposure without permanent damage. Do it. The command sequence gets finalized at hour 18 before encounter. It's a 2847-line program written in spacecraft command language. Every instruction triple-checked by separate engineering teams. One typo, one incorrect parameter, and the entire observation fails. The sequence gets transmitted to MRO at light speed, a 20-minute journey across 140 million miles of space. 20 minutes later, confirmation arrives, sequence uploaded successfully. MRO acknowledges the commands and begins its autonomous countdown. From this point forward, you're just a spectator. The spacecraft will execute the observation run entirely on its own, following instructions uploaded from a planet that won't even know if it worked until after the fact. The last 18 hours become a waiting game. Engineers run final simulations. Scientists debate what they hope to see versus what they realistically expect. Everyone knows the odds of technical failure are significant, but no one voices it aloud, because in 18 hours, 3I/Atlas reaches its closest approach to Mars, and when it does, your spacecraft's cameras will be watching, capturing data that no human has ever seen before. But first, you need to understand what those cameras are actually looking at. What does an interstellar comet look like up close? The answer turns out to be far stranger than anyone predicted. The first image arrives 42 minutes after closest approach, the time it takes for radio signals to crawl from Mars back to Earth at light speed. You're staring at your monitor when the data starts rendering, pixel by pixel, top to bottom, and what materializes on screen makes everyone in mission control go silent. 3I/Atlas glows like nothing you've ever seen. Most comets appear as dirty snowballs, with a single colour palette, white ice reflecting sunlight, maybe a yellowish dust tail trailing behind. Think of Halley's Comet, Neowise, Hale-Bopp. They're all variations on the same theme. Beautiful, yes, but predictable. 3I/Atlas. It's wearing a coat of many colours, and every single one tells a different story. The nucleus, the solid core of the comet, radiates a deep cyan blue concentrated in distinct regions. Dr. Sylvia Protopapa from Southwest Research Institute leans closer to her screen and whispers, "That's carbon monoxide ice sublimating." Sublimation, the process where frozen material turns directly into gas without becoming liquid first, is the same phenomenon that makes dry ice create that theatrical fog effect. But here is happening on a cosmic scale, with temperatures hovering around minus 390 degrees Fahrenheit. Carbon monoxide requires extremely cold conditions to freeze. On Earth, CO freezes at minus 337 degrees Fahrenheit. But in the frigid outer regions of alien solar systems, particularly around red dwarf stars that emit less heat than our Sun, carbon monoxide ice can dominate the composition of forming comets. The cyan glow you're seeing is ultraviolet light from the Sun exciting CO molecules as they boil off the nucleus, causing them to fluoresce in that distinctive blue wavelength at 451 nanometers. But here's where it gets weird. Surrounding that blue core is a rust-red halo, completely different from the Cyan center. Grisham's spectrometer breaks down the wavelengths, and the signature is unmistakable silicate dust particles ranging from 0.1 to 10 micrometers in diameter, mixed with organic compounds rich in carbon chains. These particles scatter sunlight preferentially at longer wavelengths. That's why they appear reddish. The same reason Mars itself looks red. The dust-to-gas ratio in 3 I/Atlas measures approximately 2.3, meaning for every kilogram of gas ejected. The comet releases 2.3 kilograms of dust. Compare that to typical solar system comets like 67P/Churyumov-Gerasimenko, studied up close by the Rosetta mission, which has a dust-to-gas ratio around 4.0. 3 I/Atlas is substantially cleaner, suggesting it formed in an environment with less rocky material available during its creation billions of years ago. Then there's the purple. Yes, purple, extending from the comet's sunward side. There's a distinct violet streak that shouldn't exist according to standard comet models. When the spectroscopy team runs the analysis, they find emission lines at 391 nanometers and 427 nanometers wavelengths associated with ionized carbon dioxide. But the intensity is all wrong. CO2 ions typically produce weak signatures in cometary spectra, not this vibrant purple glow that dominates portions of the coma. This doesn't match our database, admits Dr. Michael Kelly from the University of Maryland, who spent 15 years cataloguing cometary spectra. He pulls up comparison charts from 93 different comets observed since 1995. None show this purple feature with anywhere near this intensity. Something about 3 I/Atlas's chemical makeup. Or perhaps its interaction with the solar wind at this particular distance from the Sun is creating conditions never documented before. Have you ever mixed paints as a kid and gotten an unexpected color? That surprise of seeing something emerge that you didn't predict. That's the feeling rippling through the science team, except instead of paint, it's billion-year-old chemistry from another star system revealing itself for the first time. The multicolored glow extends outward from the nucleus for approximately 18,000 miles, creating a coma, the cloud of gas and dust surrounding a comet's core that's roughly twice the diameter of Earth. HIRIS's resolution allows you to see structure within this coma streamers. Jets, asymmetric bulges. The distribution isn't uniform. The Cyan CO emissions concentrate on the sunward hemisphere, which makes sense, that's where solar radiation heats the surface most intensely. But the red dust cloud shows a peculiar concentration on the comet's trailing edge, as if something is preferentially ejecting particles in that direction. Analysis of the color gradients reveals temperature variations across the nucleus. Infrared data from MRO's radiometer, usually used to measure Martian surface temperatures, shows the sunward side of 3 I/Atlas reaches approximately minus 280 degrees Fahrenheit, while the night side plunges to minus 440 degrees Fahrenheit. That's a 160-degree temperature swing across an object only a few miles wide. These extreme thermal gradients create stress fractures in the ice, and when pressurized gas builds up beneath the surface, it finds those cracks and explodes outward. Which brings you to the most dramatic discovery in the image's active jets. You count 7 distinct jet features erupting from the nucleus, each one spraying material into space at velocities exceeding 1,200 miles per hour. Some jets appear as narrow, collimated streams like water from our high-pressure hose. Others spread out in broad fans, suggesting they're venting from larger fractures or porous regions. One jet on the southern hemisphere pulses visibly between sequential images taken 90 seconds apart, brightening and dimming as if regulated by some internal pressure cycle. Doctor. Naomi Rowe Gurney from NASA's Goddard Space Flight Center measures the mass loss rate from these jets using the observed brightness and known dust scattering properties. Her calculations indicate 3I/Atlas is losing approximately 140 pounds of material every second. Doesn't sound like much over the course of its passage through the inner solar system, roughly 200 days from entry to exit. That's 2.4 million pounds of mass shed into space. The comet is quite literally evaporating as it races past the sun. But why these specific colours? Why this particular pattern of jets? The answers lie in the chemical recipe encoded in 3I/Atlas's frozen nucleus, a recipe mixed in the disk of gas and dust surrounding a star that died before our sun was born. And that recipe is about to reveal something profound about planetary formation beyond our cosmic neighbourhood. What happens when you decode the chemistry of an alien world? You discover that the rules for building solar systems might be far more diverse than we ever imagined. The jets aren't just beautiful, they're erupting laboratories, each one a time capsule exploding in slow motion. And when you analyse what's inside those eruptions, you find molecules that rewrite the story of how planets form around distant stars. Crism's spectrometer dissects the light bouncing off 3I/Atlas's jets, splitting it into 544 individual wavelengths, ranging from visible to near-infrared. Think of it like a cosmic fingerprint scanner. Every molecule absorbs and reflects light at specific wavelengths, creating a unique signature. Water shows up at 1.5 and 2.0 micrometers. Carbon dioxide appears at 2.7 micrometers. Methane has distinctive bands at 1.65, 2.2 and 3.3 micrometers. What you're seeing in the data sends shockwaves through the spectroscopy team. The water-to-carbon monoxide ratio in 3I/Atlas measures 0.8-1. Let me put that in perspective in our solar system's comets objects from the Kuiper belt. The Oort cloud, even Jupiter family comets that swing through the inner system regularly, that ratio averages 10-1 or higher. Water dominates. Carbon monoxide is the minority ingredient. But in 3I/Atlas, carbon monoxide nearly matches water abundance. It's as if someone took a standard cometry recipe and flipped it upside down. Doctor. Adam McKay from NASA's Goddard Space Flight Center runs the numbers through planetary formation models. This ratio tells us 3I/Atlas formed beyond the carbon monoxide snowline in its home system, he explains in the research briefing. The carbon monoxide snowline, the distance from a star where CO freezes, sits much farther out than the water snowline. In our solar system, water freezes around 2.7 astronomical units from the Sun, roughly between Mars and the asteroid belt. But carbon monoxide, it doesn't freeze until you reach approximately 20 to 25 AU, out past Uranus. For 3I/Atlas to have this much frozen CO, it must have formed in the frigid outer reaches of its birth system, where temperatures stayed below minus 337 degrees Fahrenheit throughout the planetary formation period. We're talking about a region so cold, so distant from its parent star, that even carbon monoxide, a gas at room temperature on Earth, condensed into ice and got incorporated into the comet's nucleus. But here's where it gets fascinating. The methane detection changes everything. Spectral lines at 2.2 and 3.3 micrometers reveal methane ice embedded in the nucleus at concentrations of approximately 1.4% by mass. Methane is even harder to freeze than carbon monoxide. It requires temperatures below -297 degrees Fahrenheit. Finding substantial methane means 3 I/8 didn't just form in the outer regions of its system, it formed in the extreme outer regions, possibly 30 to 40 AU or beyond from its parent star. Compare that to where Earth formed 1 AU from the Sun, in a temperate zone where water could exist as liquid, where silicate rocks condensed, where the building blocks of life could chemistry their way into existence. 3 I/Atlas comes from the deep freeze, the cosmic equivalent of being born in Antarctica versus being born in the tropics. Now here's a question that might blow your mind. What kind of star system creates these conditions? The spectroscopy reveals another clue: deuterium. Deuterium is heavy hydrogen, an isotope with 1 proton and 1 neutron instead of just a proton. It forms preferentially in cold environments through chemical reactions that favour the heavier isotope. When you measure the deuterium to hydrogen ratio in water molecules from 3/Atlas's jets, you get a value of 5.2 x 10⁴. That's 5.2 times 10 to the -4th in normal speak, or about 1 deuterium atom for every 1 923 hydrogen atoms. Earth's ocean water has a DH ratio of 1.56 x 10⁴. Comets from our Oort cloud average around 3 x 10⁴. 3 I/Atlas sits significantly higher. Dr. Stephanie Milam from NASA's Goddard Astrobiology Lab interprets this. The elevated deuterium suggests this comet formed in an extremely cold, possibly low-mass protoplanetary disk, where deuterium enrichment processes operated more efficiently than in our own solar nebula. Translation 3, I/Atlas, likely comes from a system around an M-dwarf star, a red dwarf much smaller and cooler than our Sun. These stars make up roughly 75% of all stars in the galaxy, but their planetary systems look radically different from ours. Their habitable zones where liquid water could exist sit much closer to the star because red dwarfs emit less energy. But their outer regions, where comets form, those are colder, darker, more carbon-rich than anything we have here. The organic molecules paint an even stranger picture. Spectral analysis detects hydrogen cyanide HCN, formaldehyde H2CO, and methanol CH3OH, all molecules that serve as building blocks for more complex organic chemistry. The HCN abundance measures particularly high, about 0.2% of the total outgassing, compared to 0.1% in typical solar system comets. Hydrogen cyanide might sound scary, it's toxic to humans, but in space, it's a chemical superstar. HCN molecules can link together to form adenine, one of the nucleotide bases in DNA. They can create amino acids, the building blocks of proteins. Finding high HCN concentrations in 3 I/Atlas suggests its parent system had chemical pathways favouring prebiotic molecule formation, even in those frozen outer reaches. Think about that for a moment. You're looking at frozen chemistry from a solar system that might have its own Earth-like planets, its own biochemical processes, its own version of whatever life means in that corner of the galaxy. And 3 I/Atlas is carrying samples of that system's raw materials, preserved in deep freeze for millions, possibly billions of years. But there's one molecule that shouldn't be there: nitrogen. Molecular nitrogen N2 is notoriously difficult to detect in comets because it doesn't absorb light strongly in most wavelengths. But MAVEN's ultraviolet spectrograph catches a faint signature at 95, 100 nanometers during the flyby, the telltale sign of N2 ionized by solar ultraviolet radiation. The presence of molecular nitrogen is a game changer. N2 requires even colder conditions to freeze than carbon monoxide. We're talking below -346 degrees Fahrenheit. If 3 I/Atlas contains N2 ice, it formed in an environment similar to Pluto's surface, or Neptune's moon Triton, or the coldest Kuiper belt objects we've ever studied. This isn't just an interstellar comet, it's an interstellar deep freeze sample from the most extreme planetary formation conditions imaginable. The chemistry paints a portrait of 3/Atlas's birthplace, a cold, distant disk around a small red dwarf star, rich in carbon and nitrogen, poor in rocky silicates, with temperatures so frigid that molecules we consider gases on Earth existed only as solids, a system utterly unlike our own, yet following the same physical laws that govern how gravity collapses gas clouds into stars and planets. But chemicals are only half the story. The jets erupting from 3/Atlas's surface aren't just releasing gas, they're revealing something about the internal structure of this cosmic wanderer. And what that structure tells you about the violence of interstellar space is both terrifying and beautiful. Imagine an ice cube sitting on your kitchen counter. As it warms, meltwater forms on the surface, drips down the sides. The melting happens gradually, predictably. Now take that same ice cube and blast one side with a blowtorch while keeping the other side in a freezer. The thermal stress would crack it apart instantly, sending fragments flying in all directions. That's essentially what's happening to 3/Atlas, except the blowtorch is the sun, and the temperature swing isn't just cold to warm, it's minus 440 degrees Fahrenheit to minus 280 degrees Fahrenheit, a 160-degree shift across a few miles of ancient ice that's been frozen solid for potentially millions of years. You're watching the high-resolution images when you notice something that makes your stomach drop. On the nucleus's sunward side, there are cracks. Not the hairline fractures you'd expect from gentle thermal expansion, but gaping fissures, some measuring up to 300 feet across and nearly half a mile long. Hiros's resolution is good enough that you can see the rough, jagged edges where ice has fractured, revealing darker material beneath. Dr. Bonnie Baratti from NASA's Jet Propulsion Laboratory measures the albedo, the reflectivity of these exposed regions. Fresh ice reflects about 60 to 80% of sunlight, appearing bright white, but the material visible in these cracks reflects only 4 to 6% of incident light, darker than charcoal, darker than asphalt. We're seeing primordial material, Baratti notes in her analysis, possibly unchanged since this comet's formation billions of years ago. That dark material, it's likely a mixture of complex organic compounds, tar-like substances called tholins, similar to what Cassini found on Saturn's moon Titan. These molecules form when simpler compounds like methane and nitrogen get bombarded by cosmic rays and ultraviolet radiation over eons. The darkness suggests 3/Atlas's surface has been weathered by interstellar radiation during its long journey, radiation intense enough to chemically alter the outer layers. But here's what really captures your attention. The cracks are propagating in real time. Sequential images taken 90 seconds apart show one major fracture extending by approximately 50 feet. That's not geological timescales, that's human timescales. You're watching an interstellar comet literally tearing itself apart as solar heating creates internal pressure that the frozen structure can't contain. The mechanism works like this. Sunlight heats the surface ice, causing sublimation, but the heat doesn't penetrate evenly. Ice is a terrible thermal conductor, about 400 times worse than copper, so while the surface layers sublimate into gas, material just inches below remains frozen. This creates a temperature gradient hot on top, cold underneath that generates enormous mechanical stress. When carbon monoxide ice transitions from solid to gas, it expands by a factor of 500. Imagine a cubic foot of frozen CO suddenly trying to become 500 cubic feet of gas, with nowhere to go except through the overlying ice. The internal pressure can reach several atmospheres, enough force to fracture rock, let alone porous cometary ice. The jet activity you saw earlier, those aren't gentle releases of gas. They're explosive decompression events, Miniature eruptions where weeks or months of accumulated pressure find a weak point and blow out catastrophically. Dr. Dennis Bodowitz from Auburn University calculates that some of the more energetic jets release gas at initial velocities exceeding 500 miles per hour, twice as fast as the speed of sound on Earth. One jet in particular shows rotational modulation. Every 8.7 hours 3 I/Atlas's rotation period. This jet brightens and dims in a predictable cycle. When the vent faces the sun, solar heating drives intense sublimation and the jet flares up. When rotation carries the vent into darkness, the jet nearly shuts off. It's like watching a lighthouse beam sweep across the sky, except this lighthouse is powered by ancient ice from another star system. Have you ever shaken a soda can and then opened it? That explosive release when the pressure finds an exit. Scale that up to planetary proportions and you have some idea what's happening inside. 3 I/Atlas every time a new jet activates. But thermal stress creates another, more insidious problem: fragmentation risk. Comet fragmentation isn't rare. Comet Shoemaker-Levy 9 broke into 21 pieces before crashing into Jupiter in 1994. Comet 73P/Schwassmann-Wachmann 3 split into more than 60 fragments during its 2006 passage. These breakups happen when internal stresses exceed the comet's tensile strength, the force required to pull the material apart. Comets aren't solid blocks of ice. They're more like cosmic rubble piles, loosely held together by their own weak gravity and whatever internal cohesion frozen volatiles provide. When you heat them unevenly, when jets erupt asymmetrically, when thermal gradients create mechanical stress, the whole structure can just fall apart. Your team runs structural integrity models using the observed crack patterns. Estimated mass approximately 1.2 is 1012 kilograms based on brightness and assumed albedo, and known material properties of cometary ice. The models project that 3/Atlas's tensile strength needs to be at least 1000 pascals to remain intact through its solar passage. For reference, ice cube ice has a tensile strength around 1.5 million pascals. Cometary ice much weaker, often just 2000 pascals, because it's riddled with voids, pores, and inhomogeneities. The math suggests 3 I/Atlas is operating right at the edge of structural failure. One more major outburst, one more thermal shock event, and it could fragment into dozens or hundreds of smaller pieces. If that happens during the Mars flyby, your spacecraft would witness an interstellar comet destroying itself in real time, a catastrophic event that's simultaneously devastating and scientifically priceless. But thermal stress isn't the only force trying to tear 3 I/Atlas apart. There's another factor, one that doesn't show up in surface images but reveals itself through subtle changes in the comet's trajectory, outgassing thrust. Every time material jets off the nucleus, it creates a tiny rocket effect. Gas molecules accelerating in one direction push the comet in the opposite direction. Following Newton's third law, every action has an equal and opposite reaction. For small comets with weak gravity, this non-gravitational acceleration can actually change their orbit measurably. Trajectory specialists comparing 3 I/Atlas's predicted path versus its observed position find a discrepancy of approximately 190 miles after accounting for gravitational influences from the Sun, Mars, and Jupiter. That 190-mile deviation comes entirely from outgassing thrust, millions of tiny rocket burns as jets fire asymmetrically across the nucleus. Dr. Davide Farnocchia from JPL's Center for Near-Earth Object Studies calculates the total thrust at roughly 0.12 newtons, about the weight of an AA battery pressing against your palm. Doesn't sound like much, but applied continuously over weeks, is enough to alter 3 I/Atlas's trajectory by measurable amounts. The comet is literally steering itself through rocket propulsion powered by solar energy. This thrust effect also induces rotational changes. Asymmetric jets create torque, speeding up or slowing down the nucleus's spin. Analysis of brightness variations suggests 3I/8'lus's rotation period decreased from 8.9 hours to 8. 7 hours over the 30-day observation window, a 13-minute reduction caused entirely by jet-induced torque. The comet is spinning faster, fracturing under thermal stress, losing mass at 140 pounds per second, and altering its own trajectory through outgassing thrust. It's a chaotic, violent, beautiful demonstration of physics operating at the intersection of thermodynamics, structural mechanics, and orbital dynamics. But all this violence, all this thermal chaos, it's not random. There's a pattern emerging in the data, a rhythm to the outburst that suggests something profound about the internal structure of this cosmic traveller. And that pattern reveals its most closely guarded secret yet. The pattern shows up in thermal imaging first. MRO's radiometer sweeps across 3I/Atlas's surface every 90 seconds, measuring infrared radiation heat emanating from different regions. Most of the nucleus hovers around -380 degrees Fahrenheit, exactly what you'd expect for a frozen object at this distance from the Sun. But scattered across the surface are 8 distinct hotspots, each one radiating at temperatures 40 to 60 degrees warmer than their surroundings. These aren't random warm patches. They're arranged in a specific pattern clustered primarily on the comet's equatorial belt, with 2 outliers near what appears to be the southern pole. And they correlate exactly with the active jet locations you identified earlier, Doctor. Yanga Fernandez from the University of Central Florida plots the thermal data against surface topology. What emerges is a map that looks eerily like a biological system, veins branching beneath the surface, connecting the hotspots in a network that suggests interconnected subsurface cavities. We're seeing a porous interior structure, Fernandez explains during the data analysis session. Think of it like a frozen Swiss cheese, where voids and channels allow gas to migrate from deep within the nucleus toward active vents on the surface. This porosity matters tremendously. A solid block of ice would conduct heat slowly, sublimating only from the immediate surface. But a porous structure, it allows solar radiation to penetrate deeper through cracks and voids, heating internal ice that then sublimates and creates pressure. That pressurized gas follows the path of least resistance through the porous network until it finds an exit, a vent, a crack, a weak point in the structure, and explosively releases. The porosity estimates come back at 60 to 75%, meaning 3I/Atlas is more empty space than solid material. It's less like a snowball and more like a frozen sponge. For comparison, Comet 67P/Churyumov-Gerasimenko, which the Rosetta spacecraft studied exhaustively from 2014 to 2016, showed porosity around 70 to 80%. But 67P formed in our solar system. Finding similar porosity in 3I/Atlas suggests that comet formation processes, regardless of which star system they occur around, tend to produce these fluffy, porous structures. Why? The answer lies in how comets form. They don't freeze as single unified blocks. Instead, they aggregate from countless smaller icy particles, grains ranging from micrometers to meters across, that gently stick together in the frigid outer regions of protoplanetary disks. Gravity is too weak at these distances to compress everything into a dense mass, so the structure retains vast amounts of void space between particles. It's accretion through gentle collisions, building a cosmic snowball one flake at a time. But here's where 3I/Atlas reveals something unexpected layering. Here is images of the exposed cliff faces revealed where chunks of broken away show distinct stratification. You can count at least 7 separate layers, each one 30, 60 feet thick, visible in cross-section like tree rings or geological strata. These layers have different reflectivity, suggesting they have different compositions or different grain sizes. Planetary formation models explain this layering through episodic accretion. As the protoplanetary disk around 3I/Atlas's parent star evolved over millions of years, the available material changed early on. Perhaps the disk was carbon-rich, creating layers dominated by carbon monoxide and organic compounds. Later, as gas giants formed and migrated, they stirred up water ice from warmer regions, temporarily increasing water abundance in the outer disk. Each distinct era of the disk's evolution deposited a layer with a slightly different chemical recipe. You're literally looking at a geological record, a stratigraphic history of an alien solar system's formation process. Preserved in frozen layers for billions of years, the thermal cycling adds another chapter to this story. Every time 3I/Atlas rotates, every region experiences a day-night cycle. Dayside temperatures peak at minus 280 degrees Fahrenheit. Nightside temperatures plunge to minus 440 degrees Fahrenheit. That's a 160-degree swing every 8.7 hours. Over the weeks since 3I/Atlas entered the inner solar system, it's experienced this thermal cycling hundreds of times. What does repeated freeze-thaw cycling do to a porous icy structure? It progressively weakens it. When ice heats up during the day, it expands microscopically. When it cools at night, it contracts. This expansion-contraction cycle creates fatigue stress, the same phenomenon that causes bridges to crack after years of temperature variations, or why your car's engine block can develop fractures over time. In 3I/Atlas's case, this thermal fatigue manifests as the growing network of surface cracks and the progressive destabilization of the internal structure. Dr. Nalin Samarasinsa from the Planetary Science Institute models this process using finite element analysis, a computational technique that divides the comet into millions of tiny elements and calculates stress on each one. His simulations show that after approximately 180 day-night cycles, which 3I/Atlas has now experienced, the accumulated thermal fatigue reduces structural integrity by 35 to 40%. Think about cracking your knuckles repeatedly. The first few times, nothing happens, but keep doing it over and over, and eventually the joint weakens. 3I/Atlas has been cracking its knuckles every 8.7 hours for the past 5 months. But temperature extremes create another, subtler effect sintering. When ice particles are held at temperatures close to their sublimation point for extended periods, they confuse together at contact points through a process where molecules migrate from high-stress regions to low-stress regions. It's like how snow left sitting for weeks develops an icy crust. Individual snowflakes merge into a more cohesive structure. In 3I/Atlas's sunward regions, this sintering might actually strengthen the surface layers, creating a harder crust that temporarily seals vents and allows internal pressure to build higher before the next explosive release. This could explain why some jets show periodic rather than continuous activity. They're pressure regulated by the formation and rupture of sintered surface crusts. The interplay between thermal weakening and thermal strengthening creates a dynamic system constantly in flux. Some regions are getting stronger while others simultaneously weaken. The comet is literally remodeling itself in response to solar heating, and you're watching this process unfold across the 48 hours of intensive observation. One more thermal effect deserves attention. The asymmetric heating creates what planetary scientists call the rocket effect, with much more complexity than simple outgas in thrust. Because the hotspots are unevenly distributed, they create differential heating across the nucleus. The southern hemisphere receives more direct solar illumination during this part of 3I/Atlas's orbit, causing it to outgas more vigorously than the northern hemisphere. This asymmetry doesn't just change the comet's trajectory, It creates a thermal torque that alters its spin axis orientation. Over weeks to months, this torque can cause the spin axis to precess, wobbling like a spinning top that's starting to slow down. Dr. Beatrice Müller from the German Aerospace Center calculates that the observed jet asymmetry could shift 3I/8's spin axis by 3 degrees over the next year. Why does this matter? Because spin axis orientation determines which regions receive sunlight during different parts of the orbit. A shifting spin axis means different surface areas will be heated, activating currently dormant regions while putting currently active jets into shadow. The comet's activity pattern will completely change as it exits the solar system, not because it's running out of volatile materials, but because the thermal landscape is literally shifting beneath the surface. Have you ever watched ice melt in the glass and noticed how it cracks and shifts as temperature changes? That's essentially what's happening to 3/8', except it's the size of a small mountain and it's hurtling through space at 200,000 miles per hour. But all these thermal dynamics, all this structural chaos, they're operating within boundaries set by the most fundamental force in the universe, gravity. And when you measure how gravity holds this crumbling iceberg together, the numbers reveal something borderline miraculous about its survival. The navigation problem hits you like a freight train when you see the numbers. 3I/Atlas is moving at 54 kilometers per second relative to Mars. That's 100,780 miles per hour, or roughly 160 times faster than a commercial jetliner. Your spacecraft's cameras need to track this target, keep it centered in frame, and capture sharp images while both the comet and the spacecraft are moving at ridiculous velocities through three-dimensional space. Here's the nightmare scenario. HIRIS's field of view measures 1.14 degrees wide. At the flyby distance of 87,000 miles, that translates to a viewing window roughly 1,730 miles across. Sounds generous, right? Except 3I/Atlas crosses that entire field in 8.6 seconds. Miss the timing by even 2 seconds, and the comet exits frame before you've captured a single usable image. But it gets worse. Much worse. MRO orbits Mars at 2.1 miles per second. 3I/Atlas barrels through space at 33.5 miles per second. The relative velocity between your spacecraft and the target is 31.4 miles per second. That's the closing speed, the rate at which the distance between them changes. For comparison, the fastest thing humans have ever built, the Parker Solar Probe, tops out at around 120 miles per second when diving past the Sun. You're trying to photograph something moving at 1/4 that speed using instruments that were designed to image stationary rocks. Dr. Alfred McEwen, HIRIS principal investigator, describes the challenge in technical terms that barely mask his concern. We're attempting to track an object with angular velocity exceeding 0.13 degrees per second. HIRIS's tracking capability maxes out at about 0.02 degrees per second for optimal image quality. We're operating 6 times beyond design specifications. Translation: you're trying to do something the camera was explicitly not built to do. The engineering team devises a solution that sounds insane on paper. They'll slew the entire spacecraft, all 4 800-pounds of Mars Reconnaissance Orbiter, using its reaction wheels to rotate the spacecraft body fast enough to keep 3I/Atlas in HIRIS's crosshairs. Reaction wheels are heavy, spinning disks inside the spacecraft that control orientation, speed them up, and the spacecraft rotates in the opposite direction due to conservation of angular momentum. It's like sitting in a swivel chair holding a spinning bicycle wheel. Tilt the wheel one way, and the chair rotates the other way. But reaction wheels aren't designed for rapid, continuous slewing. They're meant for small pointing adjustments, fine-tuning orientation by fractions of a degree. What you need is a sustained rotation of 0.13 degrees per second for the entire 8.6-second flyby window. That's asking the wheels to operate in a regime where vibrations, mechanical stress, and power consumption all spike dangerously. The power budget becomes critical. Each of the 4 reaction wheels draws 15 watts during normal operation, but can surge to 35 watts during rapid slewing. At peak tracking, you're burning 140 watts just to control spacecraft orientation, and that's on top of the 65 watts for high-rise, 50 watts for CRISM, 100 watts for the radio transmitter. Total power draw 355 watts. Available power from batteries during Mars shadow 300 watts. You're 55 watts short. Again, someone suggests reducing Hyris's exposure time to cut power consumption. Shorter exposures mean less energy used by the camera's electronics, but Dr. Sarah Milkovich runs photometry calculations and delivers bad news. If we cut exposure below 0.8 milliseconds, 3 I/Atolase becomes too dim to resolve surface features. We'll see the coma, but the nucleus disappears into noise. The team settles on a compromise that makes everyone nervous. They'll run high-rise at reduced power mode operating the camera's 14 CCD's charge-coupled devices. The light sensors in binned mode, where adjacent pixels are combined to reduce data volume and power consumption. This drops power draw to 52 watts, but also reduces spatial resolution from 3 feet per pixel to 12 feet per pixel. You're sacrificing image sharpness to make the power budget work. But there's another problem lurking in the timeline communication latency. Commands from Earth take 20 minutes to reach MRO. Telemetry from MRO takes another 20 minutes to return. That's a 40-minute round-trip light-speed delay. You cannot pilot this spacecraft in real time. Every action must be pre-programmed, uploaded, and executed autonomously. This means the observation sequence needs to be perfect before it starts. Because once MRO begins the tracking maneuver, there's no way to abort, adjust, or correct errors. If something goes wrong, a reaction wheel glitches. A sensor reports bad data. The star tracker loses lock. The spacecraft has to troubleshoot and recover on its own using pre-coded decision trees. The flight software team writes conditional logic into the command sequence. If star tracker fails, switch to gyroscope-based pointing. If gyroscope drifts beyond 0.5 degrees, halt science observations and enter safe mode. If safe mode triggers, transmit diagnostic telemetry immediately. It's like writing a choose-your-own-adventure book where every branch needs to account for potential failures. Dr. Dan Klaus, MRO's project manager, reviews the final command sequence. It's 421 lines of code, uploaded 18 hours before the flyby. We've done everything we can, he tells the team. From here, it's up to the spacecraft. 20 minutes after upload, confirmation arrives, sequence received, validated, loaded into onboard memory, standing by for execution timer. Now comes another challenge, one that doesn't involve engineering or power budgets, but pure celestial mechanics predicting exactly where 3I/Atlas will be during the flyby window. You'd think tracking a comet's position would be straightforward. Measure its trajectory, apply Newton's laws of motion, calculate where it'll be in 18 hours. Done. Except 3I/Atlas isn't following a purely gravitational path. Remember those jets? Every eruption creates thrust, pushing the comet slightly off course. And because jet activity varies, some jets pulse. Others remain continuous. The non-gravitational acceleration is unpredictable. Trajectory specialists at JPL's Navigation and Mission Design section use observations from ground-based telescopes to refine 3I/Atalas's position every 6 hours. They measure angular position against background stars, calculate velocity vectors, and feed this data into orbital propagation models. But even with continuous tracking, uncertainty remains. Dr. John Giorgini, who specializes in small body dynamics, quantifies the uncertainty. At flyby time, our position error ellipse measures approximately 180 miles along the trajectory and 25 miles perpendicular to it. That means 3I/Atlas could be anywhere within that ellipse. 180 miles might not sound like much on cosmic scales, but when your camera's field of view is 1/730 miles wide, a 180-mile position error means the comet could appear anywhere from dead center to near the edge of frame. If it appears near the edge, tracking becomes nearly impossible. The camera's pointing would need to adjust faster than the reaction wheels can physically rotate. The team runs Monte Carlo simulations, thousands of computer-generated scenarios, where they vary 3I/8 position within the uncertainty ellipse and see how many result in successful tracking. The success rate comes back at 73%, nearly 3 times out of 10. The encounter geometry fails and you get blurry, unusable images. Those aren't comforting odds when you're betting a once-per-civilization observation opportunity. Have you ever tried to thread a needle while wearing oven mitts? That's roughly the level of precision required here, except the needle is moving at 120,000 miles per hour. You're controlling your hand with a 40-minute delay, and you only get one attempt. 6 hours before closest approach, the final tracking observation comes in from the Gemini North Telescope in Hawaii. 3I/Atlas's position gets updated one last time. The trajectory team recalculates. The position error drops to 140 miles along track. 18 miles cross-track. Success probability increases to 81%. Better. Not perfect, but better. The command sequence cannot be modified anymore. It's already loaded and running on MRO's onboard computers. Whatever happens next happens according to the plan you committed to 18 hours ago. The spacecraft is now autonomous, executing a carefully choreographed dance in the darkness above Mars, preparing to capture an interstellar visitor moving faster than anything it was ever designed to track. In 3 hours, you'll know if the gamble paid off. But success or failure hinges on something beyond engineering precision, beyond computational models, beyond even the meticulous planning that went into every line of code. It comes down to whether the universe decided to cooperate, whether 3I/Atlas shows up where you calculated it would be, whether the jets don't suddenly flare and push it off course, whether a million tiny variables all align in your favor. Space exploration often feels like a battle against impossible odds. And right now, with the clock ticking down and your spacecraft hurtling toward a target moving at a significant fraction of orbital velocity, those odds feel especially impossible. But there's one thing working in your favor, something that transforms this from a blind gamble into a calculated risk. That one thing is data, mountains of it, years of it. Data that transforms guesswork into science. MRO has been orbiting Mars since March 2006, nearly 19 years of continuous operation, circling the red planet 50,000 times, photographing every crater, canyon, and dust storm. The spacecraft's navigation team knows its orbital behavior better than most people know their daily commute. They've mapped every wobble in its trajectory, every tiny perturbation from Mars's uneven gravity field, every nanometer of drift in its reaction wheel. Performance as bearings age and lubricants degrade. This institutional knowledge becomes your secret weapon. When the tracking sequence begins at T-4 minutes, MRO's Star Tracker, a specialized camera that identifies star patterns to determine spacecraft orientation, locks onto reference stars in Cassiopeia. It's measuring angles between stars accurate to 0.001 degrees, essentially giving the spacecraft perfect knowledge of which direction it's pointing. Dr. Jill Scott, lead navigation engineer, explains the significance. Star tracker accuracy is what allows us to execute this maneuver. Without knowing our exact orientation, Even the most sophisticated tracking algorithm fails. At T-3 minutes, the reaction wheels spin up to operational speed. You can see the telemetry wheel 1 at 2847 revolutions per minute. Wheel 2 at 2851 revolutions per minute. Wheel 3 at 2839 revolutions per minute. Wheel 4 at 2855 revolutions per minute. The slight differences account for bearing where Wheel 3 has been running slightly slower since a minor anomaly in 2019, but the flight software compensates automatically, adjusting torque commands to each wheel to achieve the required spacecraft rotation rate despite their individual quirks. At T-2 minutes, HIRIS begins its pre-imaging sequence. The camera's focal plane, the sensor array that actually captures light, needs to cool to -58 degrees Fahrenheit for optimal signal-to-noise ratio. Thermoelectric coolers activate, drawing heat away from the CCDs and radiating it into space. Temperature telemetry drops -20 degrees Fahrenheit, -35 degrees Fahrenheit, -48 degrees Fahrenheit, -56 degrees Fahrenheit. The cooling rate slows as it approaches target temperature. At T-90 seconds, HIRIS reports ready status. At T-60 seconds, CRISM initiates its spectral calibration routine, measuring instrument response across 544 wavelengths using an internal calibration lamp. This baseline will be subtracted from actual observations of 3 I/Atlas to isolate the comet's spectral signature from instrumental artifacts. At T-30 seconds, MRO enters Mars shadow. Solar panels go dark. Battery power takes over. Voltage drops from 32.4 volts to 31.8 volts as the battery begins discharging. Power management systems activate, shutting down non-essential heaters, dimming status LEDs, reducing telemetry transmission rate to conserve every possible watt. At T-10 seconds, the spacecraft begins its slewing maneuver. Reaction wheels accelerate smoothly, angular momentum building. The star tracker shows orientation changing 0.02 degrees, 0.05 degrees, 0.09 degrees. The spacecraft is rotating, pointing its cameras toward the predicted intercept point where 3/Atlas should appear. At T-3 seconds, HIRIS's shutter opens. The CCD array begins integrating photons, collecting light one particle at a time. At T0, closest approach, 3I/Atlas enters the field of view. It's there, dead center, exactly where the trajectory models predicted. The comet appears first as a bright overexposed core surrounded by the diffuse coma. But as HIRIS's auto-exposure algorithm adjusts, details emerge. You can see the nucleus irregular, oblong, rotating slowly. The active jets stand out as bright streamers against the darker background. The multicolored glow that amazed you earlier now reveals itself in unprecedented clarity, distinct regions of cyan, red, and that mysterious purple, each one corresponding to different outgassing chemistry. But here's what makes this moment transcend from successful observation to scientific goldmine: the resolution. HIRIS is capturing features as small as 12 feet across on the nucleus surface. 12 feet. On an object 87,000 miles away, moving at 120,000 miles per hour. For perspective, Hubble Space Telescope's best images of 2E/Borisov, the previous interstellar comet, resolved features down to about 450 feet. You're seeing 37 times more detail. At this resolution, individual boulders become visible. Surface textures emerge, some regions smooth and uniform, others rough and fractured. You can see the shadowed sides of cracks, giving three-dimensional depth to the fracture network. One crater, possibly an impact scar from a collision millions of years ago, measures 280 feet across with a raised rim that casts a shadow at the current illumination angle. The jets become spectacular at this scale. Instead of appearing as simple bright streaks, You can now see internal structure braided streams where multiple vents merge. Dusty clumps ejected as coherent chunks before dispersing. Even shadows cast by optically thick dust clouds near the vent exits. One jet shows a corkscrew pattern, spiraling as it extends outward, likely caused by the nucleus's rotation carrying the vent across different solar illumination angles during the hours-long eruption. CRISM simultaneously captures spectral data across those 544 wavelengths. The spectrometer is essentially taking 544 different photographs of 3 I/Atlas at 544 different colors. From visible light through near-infrared, when assembled, this creates a 3-dimensional data cube, 2 spatial dimensions, plus 1 wavelength dimension. Scientists can later slice through this cube at any wavelength to see how that particular color is distributed across the comet. The carbon monoxide emission at 451 nanometers shows strongest intensity on the sunward hemisphere's equatorial band, exactly matching the primary jet locations identified in visible light. But the water emission at 1.5 micrometers peaks slightly offset from the CO emission, suggesting the subsurface ice composition varies laterally. Some regions are CO-rich, others more water-dominated, reflecting the layered structure you saw in the exposed cliff faces. At T plus 4.3 seconds halfway through the observation window, something unexpected happens. One of the southern jets suddenly brightens by a factor of 3. You watch in real time as the jet's luminosity spikes, then settles back to baseline over the next 2 seconds. This is an outburst event, a transient explosive release of volatile material triggered by what collapse of a subsurface cavity breakthrough of pressurized gas through a sealed vent, structural failure of a weakened ice bridge. Dr. Tony Farnham from the University of Maryland, watching the telemetry stream, mutters. We just witnessed a cometary outburst in real time with spatial resolution better than any previous observation. Do you understand how rare this is? The data keeps flowing. HiRISE captures 127 individual frames during the 8.6 second window, each one a push broom scan line that builds up the complete image as the spacecraft's tracking keeps 3 I/Atlas centered. CRISM simultaneously records spectral data at 0.05 second intervals. The context camera grabs wide-angle images showing the full coma extending tens of thousands of miles. Even MRO's optical navigation camera, normally used for spacecraft pointing verification, captures images of 3 I/Atlas against the starfield background. At T plus 8.6 seconds, 3 I/Atlas exits the primary field of view. Hiros's shutter closes. CRISM terminates observation mode. The reaction wheels begin decelerating, returning the spacecraft to its normal Mars-pointing orientation. 16 seconds later, MRO emerges from Mars shadow. Solar panels drink in sunlight again. Battery charging resumes. All systems nominal. Total data collected 14.2 gigabits. That's roughly 1. 8 gigabytes, about as much data as 450 high-resolution photos from your smartphone. Except this data contains scientifically calibrated imagery and spectroscopy of an interstellar object at resolution never before achieved. But there's a catch. MRO's onboard solid-state recorder, the spacecraft's hard drive, can store 160 gigabits total. This single observation just consumed 8.8% of available storage, and it takes time to downlink data to Earth. At current communication rates through NASA's Deep Space Network, transmitting 14.2 gigabits requires approximately 6.5 hours of continuous transmission. Think about that. You captured 8.6 seconds of observation, and it takes 6.5 hours to send that data home. The transmission begins immediately, targeting the 230-foot diameter radio dish at Goldstone, California. Radio waves carrying the data crawl across 140 million miles of space at light speed. 20 minutes later, the first packets arrive at the Deep Space Network receiving station. Engineers verify data integrity, decompress files, and begin routing imagery to the science team. 42 minutes after closest approach, 20 minutes for light to travel from Mars to Earth, plus 22 minutes of processing and transmission, the first image appears on your screen. And everything you thought you understood about interstellar comets suddenly needs revision. Because what you're seeing in these images doesn't just answer questions about 3I/Atlas. It raises entirely new questions about the diversity of planetary systems, the chemistry of stellar nurseries light years away, and the fundamental processes that govern how worlds form across the galaxy. This data will keep scientists busy for years, decades, even as they extract every possible insight from these precious 8.6 seconds. But perhaps most importantly, this successful observation proves something that will reshape space exploration strategy going forward. It demonstrates that with enough preparation, with institutional knowledge accumulated over years of operation, with engineers willing to push spacecraft beyond their nominal design limits, we can do the impossible. We can catch glimpses of cosmic messengers as they pass through our neighborhood, even when everything about the encounter seems designed to thwart us. The images don't just confirm theories, they demolish some and create entirely new ones. Within hours of the first full-resolution data arriving, Dr. Alan Stern from Southwest Research Institute, the same scientist who led the New Horizons mission to Pluto, publishes a preliminary analysis that sends ripples through the planetary science community. His team compares 3I/Atlas's surface morphology to every comet humanity has studied up close, Halley, Borrelly, Wild 2 Temple, 1 Hartley, 2 and 67P/Churyumov, Gerasimenko. The conclusion 3I/Atlas doesn't match any of them. This object displays surface features we've never documented on solar system comets, Stern notes in the rapid response paper submitted to Nature Astronomy. The crater density, the fracture patterns, the albedo variations, they suggest a formation and evolution history fundamentally different from anything in our cosmic backyard. Let's break down what makes these images so revolutionary. First, the crater count. Planetary scientists use crater density, how many impact craters per square mile, as a clock. More craters mean the surface is older, having accumulated more impacts over time. Fewer craters suggest a younger surface, or one that's been resurfaced recently by geological activity. When you count craters on 3I/Atlas visible in high-res images, you find approximately 23 craters larger than 30 feet in diameter per square mile. Compare that to 67P/Churyumov-Gerasimenko, which Rosetta found had about 8 similar-sized craters per square mile. 3I/Atlas has been hit nearly 3 times more often, but why Dr. Luke Dones from Southwest Research Institute proposes an explanation. Interstellar space isn't empty. Dust grains, micrometeorites, even larger debris populate the galaxy. An object travelling through interstellar space for millions of years encounters far more impactors than something safely orbiting within a solar system. Think of it like driving through a rainstorm versus sitting in your garage. The moving car gets hit by more raindrops. These impact craters tell another story age. If 3I/Atlas accumulated this crater density while travelling at typical interstellar velocities around 15-30 miles per second relative to the galactic background, the exposure time calculates to approximately 40-80 million years. That's how long this comet has been wandering between stars. Your grandparents weren't around 80 million years ago. Dinosaurs were. This comet has been travelling through space since the age of Tyrannosaurus rex. Second revelation, the surface texture. At 12-foot resolution, you can see something bizarre, a network of ridge-like features crisscrossing portions of the nucleus that look eerily like dried riverbeds or mud cracks on Earth, except there's no liquid water on 3i/Atlas, no atmosphere, no weather. These features are something else entirely. Dr. Carey Lisser from Johns Hopkins Applied Physics Laboratory proposes their sublimation pits, areas where subsurface ice sublimated asymmetrically, causing the overlying surface to collapse and fracture in organized patterns. We see similar features on Mars's polar caps where CO2 ice sublimates seasonally, Lisser explains. But the scale and organization here suggest these formed over extremely long timescales, possibly millions of years of slow erosion by interstellar radiation. The ridges measure 8 feet tall and extend for hundreds of feet across the surface, creating a polygonal pattern that divides the nucleus into distinct segments. This isn't random fracturing, it's organized, almost geometric, suggesting uniform internal structure responding to uniform external forces. It's the signature of a slow, patient process, not sudden violence. Third discovery, the albedo map. When you measure how much light different regions of 3i/Atlas reflect, you create a brightness map, a visual representation of surface composition. Most regions reflect 4 to 6% of incident sunlight, consistent with dark organic rich material, but scattered across the surface are patches reflecting 15 to 20% of light, nearly 4 times brighter. Spectroscopy reveals these bright patches are water ice, fresh ice exposed by recent fracturing or outburst events. The distribution is fascinating. Bright patches cluster near active jet vents and along major fracture lines, exactly where you'd expect fresh subsurface ice to be exposed, but some bright patches appear in seemingly random locations far from any obvious activity. Dr. Sylvia Protopapa analyzes the spectra of these anomalous bright patches and finds something unexpected. They're not just water ice. They contain crystalline water ice, a specific structural form where water molecules are arranged in an organized lattice rather than the amorphous jumble typical of interstellar ice. Crystalline ice forms when amorphous ice is heated above -173 degrees Fahrenheit, causing the molecules to reorganize. This tells us these surfaces have been heated relatively recently, Protopapa explains, possibly by internal processes, radioactive decay of trace elements, or remnant heat from the comet's formation, or possibly by previous passages through other stellar systems where solar heating triggered crystallization. Wait, previous passages through other stellar systems? Yes, 3i/Atlas might not be visiting just one star system, it could be a repeat visitor, a cosmic wanderer that's made the rounds through multiple stellar neighborhoods over its 80 million year journey. Every time it passes near a star, it gets heated, loses mass, develops new fractures, and alters its surface properties. The cumulative effect of multiple stellar encounters could explain some of the unusual features you're observing. Fourth, finding the dust particle size distribution. CRISM spectroscopy allows scientists to determine not just what compounds are present, but also the size of dust particles scattering light. Different particle sizes scatter light differently. Small particles less than 1 micrometer scatter blue light preferentially, while large particles greater than 10 micrometers scatter red light. Analysis shows 3i/Atlas's dust distribution peaks at 5 micrometers, roughly the size of a red blood cell. This is significantly larger than typical solar system comet dust, which peaks around 1 micrometer. Dr. Jessica Sunshine from the University of Maryland suggests this indicates different formation conditions. Larger dust particles form when there's more rocky material available during comet accretion, or when ice sublimates more slowly, allowing particles to stick together rather than being swept away immediately. Fifth insight, the gas-to-dust ratio calculation. By measuring the brightness of dust scattering sunlight and comparing it to the brightness of fluorescence from sublimating gas molecules, scientists can calculate how much dust versus gas the comet releases, for 3I/Atlas. This ratio comes out to 2.3 kilograms of dust per kilogram of gas. Most solar system comets range from 1.1 to 6.1 with an average around 4.1. 3I/Atlas sits on the low end, relatively more gas than dust. This suggests either the comet formed with less rocky material to begin with, or B, previous stellar encounters preferentially removed dust, leaving the gas-rich interior. Either way, it points to compositional differences from solar system standards. Have you ever looked at two people and tried to figure out if they're related based on their features? That's essentially what scientists are doing here, comparing 3I/Atlas's features to solar system comets to determine how similar or different the formation processes were. The data also reveals something about 3I/Atlas's interior structure through seismic analysis. Yes, seismic analysis on a comet. When jets erupt explosively, they create pressure waves that propagate through the nucleus like miniature earthquakes. These waves travel at different speeds through different materials, faster through solid ice, slower through porous voids. By analysing the timing and intensity of brightness fluctuations in different surface regions after major outburst events, Dr. Nalin Samarasinha's team essentially performs seismic tomography. Their results indicate the nucleus contains at least 3 distinct layers, a porous outer shell extending 150-200 feet deep, a denser middle layer rich in carbon monoxide ice, and a core region that's possibly more pristine, less altered by sublimation. This layered structure matches theoretical predictions for how interstellar comets should evolve. The outer layers get processed by interstellar radiation and multiple stellar encounters. The middle layers represent material moderately altered by heating and cooling cycles. The core remains pristine, a time capsule of the original formation conditions from 4-5 billion years ago, preserved by the insulating layers above it. Every single one of these findings, the crater density, the surface textures, the crystalline ice patches, the dust properties, the interior structure feeds into a larger understanding, and that understanding changes the fundamental question scientists ask about planetary systems from "are we unique?" to "how much diversity exists in the galaxy's planet-forming processes?" The answer, emerging from 8.6 seconds of observation, is staggering immense diversity. Star systems don't follow a single template. The chemistry, the temperature, the available materials, the stellar radiation environment, all of these vary dramatically depending on the parent star's mass, metallicity, age, and location in the galaxy. And 3I/Atlas is proof that these variations produce outcomes wildly different from our own solar system. But here's the profound realization that emerges from this data if conditions can vary so much in how frozen comets form. Imagine the diversity in how rocky planets evolve, how atmospheres develop, how life, if it exists elsewhere, might emerge through completely different chemical pathways. 3I/Atlas is a messenger carrying that message written in ice. The universe is far more creative than we imagined. And this was just one interstellar visitor. How many more are out there, waiting to be discovered, each one carrying its own unique story from distant star systems? The implications reshape how we think about space exploration itself. The success of the 3I/Atlas observation doesn't just vindicate the engineers who pulled off this impossible tracking maneuver. It triggers something bigger, a fundamental shift in how humanity approaches space exploration strategy. 3 weeks after the Mars flyby, NASA convenes an emergency workshop at the Lunar and Planetary Institute in Houston. The Agenda Interstellar Object Response Protocol, 73 scientists, engineers, mission planners, and administrators gather to answer one question. What do we do when the next visitor arrives? Because there will be a next visitor. The statistics are becoming clear. Dr. Daryl Seligman from Cornell University presents updated detection models based on the discovery rate of interstellar objects Oumuamua in 2017, 2I/Borisov in 2019. 3I/Atlas in 2024, that's 3 confirmed interstellar visitors in 7 years. But these are only the ones we caught objects bright enough, travelling through regions of sky that telescopes happen to be monitoring at the right time. Seligman's models estimate the actual population passing through the inner solar system approximately 10 interstellar objects per year larger than 100 feet in diameter. Most go undetected because they're too faint, moving through regions of sky we're not actively surveying, or their trajectories never bring them close enough to the Sun to develop visible coma activity that makes comets stand out. We're missing 90 to 95% of interstellar visitors, Seligman explains. It's like trying to study migratory birds, when you can only see the ones that happen to fly directly over your house. You get occasional glimpses, but you're missing the full picture of migration patterns. The implications are staggering. If 10 interstellar objects traverse the inner solar system annually, and each one represents a sample from a different stellar neighbourhood with unique formation conditions, then we're surrounded by a constant stream of cosmic messengers carrying information about planetary diversity across the galaxy. We're just blind to most of them. This realization sparks a proposal that initially sounds like science fiction, but quickly gains momentum: the Interstellar Object Interceptor mission. The concept is elegantly simple but technically audacious. Instead of waiting for an interstellar visitor to pass close to existing spacecraft, a stroke of luck that happened with 3I/Atlas, why not launch a dedicated spacecraft designed specifically to intercept these objects? A probe that sits in a parking orbit, ready to deploy on short notice when ground-based telescopes detect an incoming visitor. Dr. Sarah Ballard from MIT presents preliminary mission architecture. The spacecraft would orbit at the L2 Lagrange point, a gravitationally stable location about 930,000 miles beyond Earth, where the pull of Earth and Sun balance out. From there, it could reach almost any trajectory within the inner solar system using relatively modest propulsion. The key innovation: solar electric propulsion. Traditional chemical rockets provide high thrust but limited total velocity. You burn fuel quickly and then you're coasting. Solar electric propulsion uses electricity from solar panels to accelerate ionized xenon gas to extremely high speeds. The thrust is tiny, about the force of a piece of paper resting on your hand, but it operates continuously for months or years, eventually building up enormous velocity changes. NASA's Dawn spacecraft used this technology to visit both Vesta and Ceres in the asteroid belt, the first spacecraft ever to orbit 2 different extraterrestrial bodies. The proposed interstellar interceptor would use an upgraded version capable of velocity changes exceeding 15 kilometers per second, enough to match trajectories with most interstellar objects passing through the inner solar system. The timeline becomes the critical factor. When you detect an interstellar object, you typically have weeks to months before it passes through optimal observation range. The spacecraft needs to adjust its orbit, accelerate toward the intercept point, and arrive with enough time to deploy instruments. Dr. Ballard's simulations show that with sufficient advance warning, at least 60 days, the interceptor could reach approximately 40% of interstellar visitors. That's better than the current 0.02% success rate of opportunistic observations. But there's a problem: detection lag. Current survey telescopes like ATLAS, the Asteroid Terrestrial Impact Last Alert System that discovered 3I/Atlas, scan the sky every 2 nights looking for moving objects. By the time an interstellar visitor is detected, confirmed, and its trajectory calculated, it's already deep into the inner solar system. The 60-day intercept window becomes 20 days or less. Mission success rate drops to 8%. The solution: better telescopes. Much better telescopes. enters the Vera C Rubin Observatory. Currently under construction in Chile, this facility will host the Legacy Survey of Space and Time LSST, using an 8.4-meter mirror and a 3.2 gigapixel camera to photograph the entire visible sky every 3 nights. It will detect objects 100 times fainter than current surveys and process data in real time using machine learning algorithms that can identify interstellar trajectories within hours of detection. Dr. Mario Jurich from the University of Washington, LSST project scientist, estimates Rubin Observatory will detect 50 interstellar objects per year, an order of magnitude increase over current detection rates. More importantly, Jurich notes, we'll detect them earlier, when there's still 10 astronomical units from the Sun. That gives months of lead time for intercept missions. Combine early detection from Rubin Observatory with the Interstellar Interceptor spacecraft's rapid response capability, and mission success rates jump to 60 to 75%. Suddenly, detailed study of interstellar visitors transforms from once-per-decade lucky breaks to routine science. The workshop participants begin sketching instrument payloads, high-resolution cameras, obviously, but not just optical wavelengths, infrared cameras to measure thermal emissions and map temperature distributions, ultraviolet spectrographs to detect atomic emissions from sublimating volatiles, mass spectrometers that can directly sample gas and dust, measuring molecular weights and isotopic ratios with precision impossible from remote sensing. Someone proposes an impactor, a small projectile that would intentionally crash into the interstellar object, creating an artificial crater that exposes subsurface material. Dr. Andy Rivkin from Johns Hopkins Applied Physics Laboratory, veteran of the DART mission that successfully deflected asteroid Dimorphos in 2022, supports the idea. We've proven we can hit small targets with precision. An impact experiment on an interstellar object would reveal interior composition, measure structural strength, and potentially trigger outgassing from buried volatiles. The estimated cost $850 million for spacecraft development, launch, and 5 years of operational readiness. For comparison, the Mars Reconnaissance Orbiter cost $720 million. The James Webb Space Telescope exceeded $10 billion. The proposed interstellar interceptor sits comfortably in the middle, expensive but not unprecedented. But money isn't the only resource required. The mission needs political will, sustained funding commitments, international cooperation for tracking and data sharing, and most critically patience. The spacecraft might sit at L2 for years before an intercept opportunity arises. Congress and space agencies worldwide need to accept that they're funding a mission that could launch in 2029, but not encounter its primary target until 2032 or beyond. Have you ever planted a tree knowing you might not live to see it fully grown? That's the mindset required for missions like this, investing in capabilities that benefit humanity decades into the future, even if the people making the investment never witness the payoff. The workshop concludes with a recommendation to NASA headquarters proceed with Phase A study of the interstellar object interceptor concept, allocating $15 million for detailed mission design over the next 18 months. It's not mission approval, but it's a start, the critical first step that transforms an idea into engineering reality. Meanwhile, 3I/Atlas continues its journey outward. By the time the workshop ends, the comet has passed Jupiter's orbit, accelerating as the Sun's gravity assists its departure. Its jets are shutting down as temperatures drop below sublimation thresholds. The multicolored glow fades. Within a year, it will revert to its dormant state, a frozen relic traveling in darkness, carrying its secrets back into the interstellar void. But those secrets won't stay secret. The 14.2 gigabits of data from the Mars flyby will fuel doctoral dissertations, research papers, conference presentations, and textbook revisions for years. Every frame of imagery, every spectral measurement, every photometric data point gets scrutinized, analyzed, modeled, and compared against theory, and somewhere in that data perhaps not yet recognized. Perhaps waiting for the right analytical technique or theoretical framework lies information that will reshape humanity's understanding of how planetary systems form, how chemistry evolves in extreme environments, and what possibilities exist for worlds beyond our own. The age of interstellar object science has begun. What started as a frantic 48-hour sprint to reprogram a Mars orbiter evolved into a new chapter of space exploration, one where humanity actively seeks out these cosmic visitors, studies them with purpose-built instruments, and assembles a comprehensive understanding of planetary diversity across the galaxy. 3I/Atlas was just the beginning. The next visitor approaches even now, untected, carrying its own unique story from a corner of the galaxy we may never physically reach. But we don't need to travel light years to study these distant worlds. They're coming to us, one frozen messenger at a time, delivered by the galaxy's celestial mail service. All we need to do is watch the sky, build the tools to intercept these visitors, and listen to the stories they tell. Because every interstellar object is a chapter in the galaxy's autobiography, and we're finally learning to read.